What we're going to be taking a look at today is a volume of revolution. This is slightly different from the cross sections. In a cross section, you are looking at the area on a graph, and that is your basically the flat part of this three-dimensional object. If you could take the object and set it down on a table, the surface that's in contact with the table is the same surface that is represented by the region R that's in this graph. So what's sitting on the table would be that particular region. With a volume of revolution, we end up with a cylindrical or sometimes a almost a sphere type of object that doesn't sit flat on the table. Instead, this same blue highlighted region in there is actually going to be rotated around an axis to generate the shape. So if we just look at some flat models to begin with, over on the left-hand side, we have our cross sections being squared, or of squares. And you can see that our region R, I'm going to highlight it, is that region right there that's sitting flat on the table. And then all of the squares come up off of that flat surface. What's happening with the solid of revolution on the right-hand side is we're taking that same region R and it's actually being rotated around the x-axis. So one of the main difference between the cross sections and your solids of revolution is that your cross sections are not really going outside of that region R. They're just coming along the z-axis three-dimensionally out of the graph. With the solids of revolution, we're actually taking that area and moving it all throughout the graph over a rotation around a particular axis, and we make a much larger shape that is going to be round, and there's not really a whole lot of flat parts in relation to the xy plane. Here is a visual of the solid of revolution actually being formed. So we have our area, which is given by 4 times the square root of x going down to the x-axis. That's our region R. When we revolve this around the x-axis, that region is going to pivot up out of the first quadrant and swing around. We're going to intersect with the fourth quadrant and go into our negative z space and then come around again to group that up, to meet up where we were left off. So we can actually watch this being rotated around and coming back to where we started. And that's creating our solid of revolution all the way around. So using this example, we're still going to have cross sections that are circles as we did before. So if we look at the very edge of this graph, like we had the squares over on the side, over here we do have a circle that is a cross section. But what's unique about the circle is that a radius is what's being formed here in this region R. So before, if we looked at our two-dimensional graph, the distance from our function down to the x-axis represented one of the sides of our polygon. This time, that same exact rectangle or that same line represents the radius of the circle that we're being created for each cross-section. So when we consider our generic formula that we had over to the side, where we had that capital B was the area of our cross section, that capital B is now getting replaced with an area of a circle. And that's where we're creating this formula here, that the pi r squared is the area of a circle, and that's essentially replacing what the area of our cross section would be in our previous examples. So we're setting this up when we're creating an axis or a volume of revolution or a solid of revolution. We're going to have the integral from a to b of pi r squared dx. R is going to be the radius that is found from your function down to the x-axis. Now, we also talked about how areas don't have to be sliced up according to the x-axis. We can also take a region and rotate it around the y-axis instead. And when that happens, we do need to make sure that we are in terms of y. So that means our integral will end in y. We're going to have c and d as our limits, which will be y coordinates about where the solid is going to start versus where it ends. And we're going to make sure that the function we have in there is in terms of y as well. So we're going to take a look at two examples of how these functions kind of come around and how these volumes happen. So we're taking a look at the region under a graph of y equals x to the 1/3 from 0 to 8, and we're rotating about the x-axis. So if we sketch a quick picture of what this looks like, the cube root of x comes up and around like this, and we're going to go from 0 to 8. And we're rotating it around the x-axis. So sometimes I like to draw just a little circle, kind of saying that we're going to rotate this around that particular axis. So the region that's actually being rotated, or the section that's being rotated, is this one right here. And if I think about what that's going to look like from my axis of rotation up to my function, this would be an example of one radius that is going to be swiveled around the x-axis to create one full circle. So it's almost going to look something like this when we rotate that line around in a circle. So what we're going to set this up as is the integral of our pi r squared dx. We're going to use x because we're rotating it around the x-axis, and that's how the slices are going to be created. And our limits will be from x equals 0 to x equals 8. So in our case, the r that's being dictated here is going from our function y equals x to the 1/3 down all the way to y equals 0. So the r that we have here is x to the 1/3 minus 0. So we're looking at the integral from 0 to 8 of pi times x to the 1/3 squared dx. So the antiderivative is going to have x to the 5/3 times 3 over 5, and we've got our constant pi, and we're evaluating this from 0 to 8. So we're looking at 3 pi over 5 times 8 to the 5/3 minus a total of 0 when we plug in that x equals 0. Cube root of 8 would be 2. 2 to the 5th would be 32. So we're looking at 3 pi over 5 times the 32, or a total of 96 pi over 5 is our area of revolution. So our next example is rotating it around the y-axis. So the region in quadrant 1, so we're only going to work with the x and y axis and everything in quadrant 1. We have the parabola 4 minus y squared, which is going to start up here with a y-intercept of 4, and then come down and intersect here, 0 at x equals 2. And we're rotating this around the y-axis. So we're going to rotate it around there. So the region we're talking about is this region in here. So this orange section is the one that's going to be rotated. And when it is rotated, this is going to form the radius. And it's going to swing around out in front and then come behind here and then come right back. And that's the circle that we're trying to use as almost like our cross section in this case. So we're going to have an integral that was going to end in a dy because we're rotating around the y-axis and we're slicing up according to y. So this function on the outside is y equals 4 minus x squared. I'm going to need to rewrite that in terms of y. So off to the side, we're going to say that we have y minus 4 equals negative x squared. So we can say 4 minus y is equal to x squared. And we're looking at plus or minus the square root of 4 minus y equals x. Since we're working in quadrant 1, this would only be positive because we're dealing with both positive x's and y's. So the function we're going to use is 4 minus the square root of 4 minus y. That is going to represent our radius. Our radius is going to go from the square root of 4 minus y. It's going to go to the y-axis, which is x equals 0. So here we're looking at pi r squared. So that's going to be the square root of 4 minus y, quantity squared. We're going to need to know our limits as well. We're starting at the x-axis, which is a 0, y equals 0, and ending all the way up at a y-coordinate of 4. So we're looking at the antiderivative of pi times 4, which would be pi times 4 times y, and the antiderivative of pi times negative y, which would be negative pi over 2 y squared, evaluated from 0 to 4. So when we plug in 4, we're going to end up with a 16 pi minus a pi over 2 times a 16 minus a total of 0. So we're going to end up with 16 pi minus an 8 pi, or 8 pi in total. Now there's no official units to go along with any of these problems, so we're just going to leave our final value as our final answer.